Multiple Level Feedback Queue Scheduling (MLF-Queue) Algorithm. Example: suppose an operating system uses the MLF-Queue scheduling algorithm to schedule tasks. This algorithm consists of 3 queues, each with a different priority level. The highest priority queue uses a round-robin scheduling algorithm with a quantum time of 6 units of time. The second highest priority queue uses a round-robin scheduling algorithm with a quantum time of 10 units of time. The lowest priority queue uses a preemptive short job first algorithm. A boosting time of 100 units of time is defined. When the boosting time is reached, all processes in lower priority queues are upgraded to the highest priority queue. 4 processes A, B, C, and D, with burst times of 75, 55, 17, and 23 respectively, arrive at the ready queue of the highest priority at time 0. Process A moves to the burst state as it has the lowest process ID. Once the quantum time is reached on the 6th unit of time, Process A moves to the second queue. Process B now goes to burst state, then Process C and Process D, with total burst time is 24 units of time. All processes are in the second queue, and no other processes are on the first queue. Process A moves to the burst state, and once the quantum time is reached on the 10th unit of time, Process A moves to the third queue. Process B now goes to burst state, then Process C and Process D. The accumulated burst time so far is 64 units of time. All processes are currently waiting in the third queue, while higher priority queues are empty. The processor will start processing jobs in the queue, and since the last queue is preemptive shortest job first, we will start with Process C. It will be processed in 1 unit of time and then exit the queue. Next, Process D enters the CPU and is processed in 7 units of time. Then, Process B enters the CPU and starts processing until it gets preempted at the 77th unit of time, when Process E arrives at the ready state of the first queue. Process E is processed in 3 units of time and completes. Then, Process B enters the CPU again and gets preempted when the boosting time is reached at the 100th unit of time. Now, Process A and Process B get promoted to the highest priority queue. At this time, Process A enters the CPU as it has a lower process ID. It is processed for 6 units of time and then moves to the second ready queue. Then, Process B behaves the same. The remaining burst time of Process A is 53 units of time, and Process B is 8 units of time. Process A enters the CPU, and after 10 units of time, it moves to the third queue. Process B enters the CPU and is processed and completed in 8 units of time. The only remaining process now is A with burst time equal to 43. As higher priority queues are empty, Process A enters the CPU and completes at 173 units of time as no other process arrived during the process execution. MLF-Queue is a popular scheduling algorithm for modern operating systems, i.e. Android, iOS, etc., because it can effectively balance the needs of multiple processes. It is particularly well suited for systems that need to handle both interactive and non-interactive processes. To summarize, MLF-Queue emerges as a powerful scheduling algorithm that excels in managing multiple processes, prioritizing responsiveness, resource utilization, and starvation prevention. Its dynamic nature and adaptability make it well suited for diverse systems, ultimately enhancing overall performance and user satisfaction.